For example, we have this block index XYZ and thread index XYZ. So what we need to do is, let's say we have a global 2D index. We just flatten this thread index, this nested thread box.
Sorry.
I've
just unmuted them. Do you want to ask them if they can hear you? Are they like listening live?
Yeah. Could you please check whether it sounds? I didn't know.
No, that's the thing. I lit this up and these two are both red.
Okay, got it. Yeah, perhaps just wait here a bit. Yeah. So in here we try to convert this thread index into a 2D global indexing or coordinators, x times. For example, in here you have thread ID x, right? And this is corresponding, for example, here. And to get this index, x index in global 2D coordinate. Okay. Got it. Thank you. Yeah. So in this thread ID, so you basically need to accumulate, let's say, in here is the block index here. So what you need to do is basically, you will need to know how many thread blocks along the x dimension, how many blocks you already iterate through. So you kind of multiply this block ID x with this block d to get like how many thread blocks you have iterate through. So this is how we get this 2D index. And the same for y, right? So if you, let's say, here is 2, 3. So you basically need to know in the y dimension how many thread blocks you have already iterate through. So you basically have block index y times block d times y, and plus the thread index at y. And when you convert this 2D into 1D, so you basically just multiply this y with this like how many elements or how many threads in one row. So you kind of map this 2D to 1D. So this is just an example of how you map this thread index into x and y coordinator in a 2D global coordinators, and how it maps to 1D index. So by allowing this kind of thread mapping, what you can do is you basically allows you kind of controlling multiple threads and control how each thread is performing its computation. And it's this kind of programming model is very kind of suitable for example, video processing. For example, you can kind of assign one thread to one pixel, and because in video processing you have massive amount of pixels needs to be processed, so you just have, for example, one thread blocks to one frame to processing multiple pixels in parallel. And you also have one grid, which means in the one thread block you already is processing one image. And if you need to processing multiple frames together, you have this grid idea. So this is just one example for video processing, and this SYNC-T programming model is also widely adopted by, for example, image processing. So in this case, one thread blocks might only will be only in charge of one image tile. And you also have this graph processing, so which means you kind of separate your different vertex into small groups, and each group will be handled by one thread block. So this is basic programming model, and the next we will introduce the GPU architecture. So the reason why we didn't just immediately introduce the CUDA matrix multiplication example after this is because to understanding this matrix multiplication example better, we need to know some underlying GPU architecture details. For example, what is swap? For example, what is the shared memory? So when you need to know these architecture details, until we can understand the full CUDA matrix multiplication example.
The same sort of ideas apply to other vendors' hardware, like non-CUDA GPUs.
Yeah, like for example, for OpenCL, so they use the idea of the wavefront, which is very similar to thread block. Yes. So next is the GPU architecture. So the right-hand side of this slide is showing the GPU architecture. To make this simple, I use the early version of one streaming multiprocessor. So because they don't have the tensor core, so this is just a very simple early version of GPU architecture. It looks very complicated, right? But don't worry about this. I will kind of break down into one part by one part to help you to understand. So, for example, in this GPU architecture, there are several main parts. The first one is the CUDA core, so which is shown in here, all the green parts. So they have massive amount of CUDA cores, like forming in an array. And you also have load store units, because let's say if your memory is here, right? So you kind of need to load data from a memory, and this load store part will be like in charge of how to kind of load data from this memory and feed the loaded data to different CUDA cores. So this is the second part. We have the load store units. And the third part is the special function unit. So if you remember, which is shown here. So if you remember in the first few lectures, we introduced the softmax. We have different exponential operations, and later we'll introduce all these exponential operations are actually performed in this special function unit. And this architecture, as I mentioned before, the picture showing the slide is just one simple example of GPU architecture. So it's kind of changing this GPU architecture generation by generation. For example, later on they have tensor core, and they also have TMA, the tensor memory accelerator, and they also have like different compute unit for different precisions. For example, they have different compute core for FP32, for FP64. They are representing different computational resources for different precisions. And if we zoom in this CUDA core, we can see it's basically in this Fermi architecture, it's one FP unit, for example, FP32 units, and one 8 unit. So you also have different operands collectors and dispatch ports, which means when you got the data from your load store unit, you will also need to do some like control to see at which clock cycle I need this data, and it's kind of do some control. And they also have this result queue, which means when you want to kind of like streaming out your design, how this result queue can help to manage this output streaming. And the second part is this special function units. So as I mentioned before, some complex mathematical function will be implemented in this special function unit. So the last one is now, because in the first part we mentioned this, all the green parts can be separated into 3 subparts. So you have CUDA core, you have special function units, and you actually also have this load store unit. So for this load store unit, the architecture at high level looks like here. So you have the regist file, and each CUDA core actually has its own address space for this register file. So you can kind of assume, okay, each core they have like different register files attached, different registers, and this load store unit help to load the data from either shared memory or global memory from all these lower level memory hierarchies to this register file, and this register file will feed the data to the compute core. So this is the load store unit. And here I give an example of the instruction of data load. So basically, you have these registers, RB1, which is holding the address in the global memory. And basically, for example, is pointing someone here, right? It's pointing somewhere here. And what you need to do is, so basically you have this load, data load. So you just kind of transfer the data from a global memory to your register file. And the R1 is the destination register to receive, for example, these 32 bits, because here you use the U32. It's the 32 bits value. So this is just an example of the function of this load store unit. And now we cover, if you look at this complicated GPU architecture, we already cover all the green parts. And all the green parts, they're representing different compute resources. And they also have the load store unit to control, for example, how data are loaded from for example, the lower memory hierarchy to the register file. And next, we will introduce these different parts, these different shared memory and cache. And we'll use another GPU architecture to explain the GPU memory hierarchy. So basically, in the GPU memory hierarchy, as we mentioned last week, we will have different register files, right? And we have this L1 cache, or we also know it as the shared memory. And basically, in your CUDA program, you can use these. You can explicitly control this shared memory, which we will introduce later. And you also have the L2 cache. You also have the global memory. And this L2 cache is usually not visible to programmers because they are automatically handled by runtime system. And it's more like equivalent to if you write a C code in CPU, you're not able to control how the L1 cache and L2 cache are managed. And this different memory hierarchy representing different trade-off, as I mentioned in the early of today's lecture, and also in the lecture last week. So for register file, it usually has the highest access speed. And later we have this shared memory, which has the smaller memory capacity in this GPU architecture. And the data access speed is slower than this register file. And we also have L2 cache, which has even slower data access speed. And we also have this global memory, which has the largest memory capacity, but with the lowest data access rate. For example, you might need 100 clock cycles. This is just an example. It's not the exact number. So let's say you have 100 clock cycles to get, for example, 4 terabytes data. And one thing I want to mention here is, apart from this memory capacity, the access granularity is also different in this memory hierarchy. So when I say access granularity, which means, for example, each time when you want to access this data from this GPU memory hierarchy, let's say in the global memory, each memory transaction size is basically, let's say, this is just an example, 1024 bytes. And let's say for the shared memory, you actually don't have this kind of wide transaction memory bandwidth or transaction size. So this is one thing you need to know. So in terms of the access granularity, so when you access data from the global memory, so the transaction size is usually wider than, for example, a shared memory. So I highlight here because later on we will learn a concept called memory collapsing, which is related to this concept. So if you see this memory hierarchy in this GPU architecture, you can see, for example, shared memory is corresponding to this light blue part. And you also have register file, which is corresponding to this deep blue part. Right? and you also have different other lower memory tiers. So this slide just helps you to understand, although this GPU architecture look very complicated at the beginning, but if you try to break it down, it's actually very simple, right? So you have different, the green part is different like compute resources, and the blue parts are different memory resources. Okay, so I think we will kind of have a rest for around 10 to 15 minutes, and if you have questions, you can just come forward. Yeah, we will start around 12.
I'm not going to climb on Thursday because
Really? Has anything happened today? Today? Yeah.
Oh, yeah, they are.
Ah, yes.
The other way.
I do like.
There's tomorrow.
Maybe they're deep.
Not like loads of content who sort of like a massive CDN of how loads of companies sort of cloud and also protection, like DDoS protections, like there's a gateway, so all your traffic goes through them and reported to your servers. A lot of the features you see on websites is powered by cloud. The whole thing. They do a lot more than that now.
And you paid for. Isn't GPU registers and all?
Postman. It has a good quality.
The gym membership. It's C sharp. That means that you're having the sharp for this term. It's really just like.
Also in the
Should top bigger, but cumulative.
There's many of them.
I gotta learn some
Yes, but
If you look at the specification.
How much is the unit on that?
just like asking. I'll ask him.
No, like,
They give student discounts annually. This is like in addition.
what do you pay when you?
I think it was like 10% off or something for students. For like an 8
Plus.
thing per console, and then I went to like I think it's like I always got a student discount there.
Very good C++.
What's the most interesting?
I haven't gone to the one in the real. Doesn't look bad. It's hard. I didn't get like a close look.
You put the wrong course.
I feel like it's cheap. That's why I'm like.
No, I don't know. I don't know. I'm more interested.
when
I
we
guess
do, like, the
you're doing it regularly, maybe because you get a bit bored of it.
And I have one like
I haven't seen it.
it's like where you get your place. They have like a rock climbing gym. So it's gonna be so gonna crush them. UCL, bro.
I wanted to go in and like see it, but then the door was locked, and then I went into like the main gym thing. So it's like me playing volleyball, and then the climbing wall was here, and I was
I
like,
lost 30 to 0.
that's like I saw it.
Okay. So they're like Chico.
Looking bit like the castle.
Teams play a mixed tournament. It's like, and this is
Pretty much, it's like
then there's like an
like,
actual
like you know how big like a standard like, board is for like
thing
that.
going on right now, but
So it's like that, and then it's like just covers one end of it.
so I'm not even doing that, but I'm doing both.
Yeah, I mean,
80 pounds for like.
that's London.
It's like a
No, it's just small.
No, bro.
You pay like.
ring. We can
There's the
That's not cheap. having to take the two. What did you say? Earl's Court. Yeah.
But like, if you look at like A100,
So the two architectures are different.
Using it's on the Piccadilly line, so I like live like a 5-minute walk.
I woke up today and I was like,
5-minute walk.
like the Margaret.
In the examples he's using, there's like a good state of the
I woke up, it never.
Just like so many of these words that I'm like not even. I should look at like
Beat the chair.
really make a bigger breakfast. Yeah, only time for
It's very funny if you got her like that's just so long.
yeah, dude. I'm like I don't want to get
Because I think given half you're gonna be
Yeah, like if Aaron was here, like he could do like
today, yesterday.
for that is I pack it.
like you just got here. How'd you?
Yeah, no, he could do
I'm still using ChatGPT.
I laughed I went and had to like show with
Let's go like that. You're still recovering. I was like starting to. I feel like it's only bad when I wake up. Now it's so how I feel. I spoke to some PC guys just like scratching. Sorry, they're like put it that way. Yesterday, like just like the fifth group just doing the math for ML like
platform. Oh shit, okay. I pictured it
on it like
never mind.
it's just very
Luckily it didn't.
like I mean I spent like so that was the thing I had to do that pretty much. And then there's like 4 concept 0 1 so my team is not much. Try and finish concept 0 1.
It also has like
Yeah, so they concepts like
Yeah. And also like,
yeah, all the I think it's just that science software.
he like wrote behind it. Asked by a weird
number. Oh, you have okay. Yeah. It's like how does it work? It's like once you start off with like
But I saw it. But it's like, bro, like, I think I would walk.
Some people like just
You could use anything.
I don't know. I really think it's 6. I'm not.
Like, dimensions I don't have such a.
It is interesting.
How I have
Having like too soon.
Had my schedule and now I got
By the time you graduate, might be this.
The heavyweight.
Explain what.
Earlier.
The notation is just like so much input. Some of them are just
There's going to be very standard ones in like yeah, there's just like there's this. I'm not sure which one I want to go. I guess he could. There's going to be some nice. Like,
the only one I tried to learn just
but it's kind of what I've been
probably the easiest.
I also applied to some new ones.
Nothing I hear. Sometimes you have to wake up to get to uni.
Yeah, I can't like control
How to get here.
it's just too expensive.
Yeah, that's all the one.
I always think it's
Hands.
Well, I can
Confused what was going on because I
I always think it's so cool.
like suddenly it was like
the summer.
evacuate the normal. Because it's never normally that like.
I don't know. My opinions.
But I'm the first stop on the Northern Line.
I was just like switching.
You've got like a C. It's good when you like get to sit down first. When you're sitting down, you actually don't even know this. Like such like a like so you're like realize that when you're sat down, it's like then I switched to that Victoria that Piccadilly. Like like a lot when you just shove it. On a Monday, no one's myself. They'll go for the. He doesn't just do. No, and it's on the Northern Line.
He had a fan.
Whether the individuals.
I don't play. I
feel like London is also like
It's good as well. The thing is, I think a lot of people say that.
Yeah, I know we should. Switch to Victoria.
Use an LLM to
It's just like what about
3 minutes, but you have to like keep changing. Actually, I used to.
I'd always ask.
That's true. I was like, if I got my C, I want to keep it 2 years.
Yeah, I mean, I wasn't thinking like,
We have it.
but like roughly.
I was like thinking about like I don't know this stuff.
I'm every day of the week.
I don't know.
Yeah, but I'm not in every day, so.
Yeah,
I mean, you sometimes like.
I think I looked into
Have any
it.
chance to do
For me, like for example, traveling around like I think there's gonna just be a big
I know.
research.
It's like you guys are like.
Some way of making it.
Saturday night.
Sure, I mean, I feel
I feel like it's like gonna.
you have to go out and make money. Let's make sense of it.
Real number one.
Hi, welcome back. So I hope the first hour went well. So if just because this is the first time we we run this module, and I don't know the background of different students, so if for some parts you think the pace is too fast, just let me know. And if you have any questions, if we have time, just raise your hands, and I will answer a question during the class. And as we mentioned, after this memory hierarchy, we will introduce, for example, what is the memory structure of this register files. So usually, the register file is constructed using different memory banks. So some students might ask, why is just one memory bank? So the reason is, if you have multiple parallel memory banks, you can kind of enable parallel read and write, right? Let's say you just have the 4 kilobytes memory. So what you want to do is you want to separate these 4 kilobytes into multiple memory banks, such that you can increase your memory bandwidth when you're trying to access this shared memory. So this is what we call memory bank. And in this register file, we have a multiple memory bank, and that is an arbiter, which, for example, if you have multiple memory requests, this arbiter, which is a hardware module, will help you to kind of decide which memory transaction you should go first. And you also have the crossbar, because, as we mentioned before, multiple CUDA core are connected to these shared register files. So we need a crossbar to kind of routing the data to the correct CUDA core location. So this is the structure, memory structure of register files. And so there's a convention in CUDA programming. For example, each CUDA core has its own register space. And so the maximum number of register per thread is typically 256. And you will need some like during our lab session, you will kind of need this kind of information to optimize your kernel design. And as I said, these register files are split into multiple memory banks, and you have the arbiters and crossbar to do like the memory control and data routing. And for this is the register files, and also for L1 or L1 cache, and we also call it shared memory. They are the on-chip SRAM-based memory. So remember, in the last slide, in last week, we introduced SRAM is kind of give you fast access, but it's slightly more area expensive compared with DRAM, right? So SRAM is the 6 transistors, and DRAM is 2. So this SRAM is shared within the thread block. This is very important. Please keep this in mind. So the SRAM is shared within the memory block. So the part of the reason why this is very important, because it kind of restricts you what is the theoretical max number of thread blocks in your program. So we will have some tutorial question related to this, but in here you need to remember this. So the shared memory is kind of shared within the thread block. And the access latency is usually 20 to 30 clock cycles. And some students just came to ask, now you have multiple threads, like you must have some race condition. So here is one example of, let's say, you have multiple threads. And these multiple threads, they might have conflicts in access memory banks. So let's say, let's assume, just do some assumption. So for example, each bank, we have the access width of 32 bits. Let's say this is 32 bits. This is 32 bits. Okay, so we have each bank can only be accessed by one thread at one time, and this thread also try to access 32 bits at one time. So the issue of memory conflicts, it means at the same time when you run these multiple threads together, and because these multiple threads they are running in parallel, let's say the thread 0 and thread M, they are trying to request access for the first memory bank. However, because thread 0 and thread M, in this clock cycle, each of them needs 32 bits, right? So, but in here, you only have one port for 32 bits. So which means you will need to do some serialization, which means, let's say, as I mentioned before, there's an register file arbiters which can kind of decide which threads access this memory bank 0 first. So this is the problem of memory bank conflicts. And in your tutorial question, we will have this related question to ask you like how to analyze this register file access and in the setting of multiple memory banks. And we also have add to cache, global memory. So global memory nowadays they use the high bandwidth memory, and this is some students came to ask me what I mean as because when we have the memory hierarchy, I mentioned this transaction size, right? So here I use another example to explain to you why the lower level memory hierarchy will have the wider transaction size and why this will cause the problem. So let's assume in this case, we have this so let's assume here we need to read this bunch of data from global memory to our register file. And let's say one of this chunk is 1024 bytes. 1024 bytes. So here we have 4 chunks of 1024 bytes. So in the ideal case, what we want is we kind of load so in each memory transaction, we load all the data we want. So this is the ideal case because the data is stored in the continuous address space. However, if let's say in some cases, one transaction size cannot, for example, one transaction cannot access the data from continuous address space. For example, in one case, let's say one of your threads, what the data it wants is kind of this part and this part. So they're kind of not consecutive together. So which means if you want to still get these two blue part, what you need, in the original case, you just need one transaction, right? Memory transaction to get this blue part. But in this case, because the memory transaction is trying to get data from continuous memory address, what you need to do is you first need to get the data, let's say from here, right? So you get some data you don't want, and you kind of throw it away, and then you kind of access the next continuous address space, and you also keep the part you want and throw the other part away. So that means it will kind of waste some memory bandwidth and make your memory access less efficient. Yeah.
Is the data layout something that we manage on host code, or is that something that's managed on device?
This is host by device, yes. So you basically, this is related to the data layout or memory layout of your data. So yeah, this is managed by the device side. Yeah.
Just a question about the transaction size. So does the L2 cache have a lower transaction size than L1, or is it the other way?
Usually the L2 cache has the higher transaction size, but as the CUDA programmer, so we are not able to get access to this L2 cache. So what you can control is only, for example, this global memory and this L1 cache shared memory. So it like the detail, at least it's not helpful for you to optimize the kernel, even you know this. Yeah. Yes, so this is the memory access. Remember, this transaction size is very important because one memory transaction can only access the data in continuous memory address. And the next is the idea of warp. I think some students just came to me asking, okay, they heard about this idea of warp, but this idea of warp is actually not a programming concept. It's actually a hardware concept. So which means, let's say you have a thread block. Let's say you have 1024 thread blocks you create in your CUDA program. And in your underlying hardware, so actually you use this warp to manage these thread blocks running. For example, if you have these, let's say, 64 threads in one thread block, in the real hardware execution, these thread blocks with, let's say, 128 will be divided into multiple warps. Let's say if the warp size is 32, so you will have 4 warps to manage in the hardware. So this is the warp, the idea of warp. So it's more like the hardware level implementation. And in the CUDA program, you're not able to control this warp. But when you try to use this multi-threading and use the thread index, keeping this warp idea in mind can help you to optimize your kernel, which we'll introduce later. So the idea of the warp is comes from the thread management. Let's say in this SCT programming language and in your hardware, you have 1,000 threads. However, allocating one, let's say, thread manager for each thread, it will cause a large amount of hardware overhead. Like you will increase the area and power a lot. So to save this kind of thread management, they kind of group, let's say, for example, 32 numbers of thread into a warp. So in the hardware implementation level, they will use this warp as, like for each warp, they have a warp scheduler to control this warp scheduling. And so the side effect of warp execution, so also the reason why you need to learn this concept of warp, is sometimes will introduce some warp divergence if you're not aware of this idea of warp. Let's say you have a program with some control flow, and which is showing here. So you have totally 8 threads, and for the first 4 threads, you want these first 4 threads to perform some computation, and you use some if-else condition to control the rest of 4 threads to perform the other computation. And because this number of threads in each branch is kind of less than this warp size, what you can do is you can only do this thread divergence, which means in the real hardware, so it will kind of do some like thread divergence, which means the execution of 2 thread string will be separate and serialized, which means, for example, in here, the first 4 threads, you will have these 4 threads executing some computation, and you will keep the other threads idle. And then, when you finish the computation of the for example, the first 4 threads, you will kind of come back to process the second 4 threads. So it kind of introduces some inefficiency when you kind of are not aware of this idea of warp. So when you do this CUDA programming, you need to always keep in mind, okay, what is my warp size and how to avoid this warp divergence, because this warp divergence will cause, as we notice here, a lot of idle cycles and will cause some hardware inefficiency. So this is the idea of warp. And from the, as I mentioned before, from the CUDA programming model perspective, so you are not, like you, at most of time, you cannot control this warp level scheduling. However, in some recent, I will show later, like here, in recent, for example, CUDA 9, so they introduced some warp level primitives, but this is kind of new feature. In most of cases, you are not able to control this warp level. And what you need to do in this warp is, when you do this thread block, when you design these thread and thread blocks, ensure that you can avoid this warp divergence. And when you know like what is the number of threads in this warp, you will kind of avoid this warp divergence. For example, here you will not write this if-else condition like this, but like you can allocate more computation in the, for example, in the first if-else condition. Let's say perhaps you can kind of schedule some other computation in the first 4 threads and make it as a warp. So you will not have this warp divergence anymore. So so this is the second concept you need to know. So for GPU architecture, you will have this warp. And in the hardware execution, all the threads, they are executed in a warp granularity. So knowing this concept can help you to better design your your multi-threading program. And the other idea is this tensor cores. As I mentioned multiple times in this lecture. So now we are facing the slowing down of Moore's law. We need to use the domain-specific acceleration or architecture to keep the performance boosting. So in here, NVIDIA, they also have this idea. So since the Volta introduced in 2017, so they also introduced this tensor core, which is used to perform the half precision matrix multiplication, MMA, HF MMA. So because the key computation or the most intensive workloads in AI is matrix multiplication, they kind of design this specialized tensor core for AI workloads. And if you look at this, if you have access to our slide, so this link actually introduced the evolution of tensor core. So here I just put a brief introduction of this evolution of tensor core. Sorry, it doesn't work. Sorry, my slide doesn't work. Yeah, so I will give you a brief introduction on the evolution of tensor core, which is here. So in the first generation of Volta architecture, they only support 4x4x4 matrix multiplication per cycle, because these specialized tensor core if you allocate more compute resources in tensor core, it kind of eats more area budget. So at the beginning, they kind of very conservative. They only put the 4x4x4 matrix multiplication as the specialized compute core for matrix multiplication for half precision, as I mentioned before. In the second generation of Turing, or second generation of tensor core in Turing architecture, they support different precision. They also support integer 8 and integer 4. So in the later of our lectures, so we will introduce the quantization, which means even you compress your weights from FP32 to, for example, 8.8, you will not sacrifice your algorithmic performance. So it's actually a very, very good way to kind of improve your memory efficiency, because previously, let's say, given the certain memory bandwidth, if let's say 1024 bits per clock cycle, and if the data is 32 bits, the number of elements you can get will be much less if the data element is 8 bits, right? So you kind of effectively improve your efficiency of the memory bandwidth by four times if you reduce the bandwidth from 32 bits to 8 bits. So in the second generation of tensor core, they kind of support the integer 8 and integer 4. And in the third generation, they have more features. One of the most important features is they support the sparse matrix multiplication. And this is related to another concept we will introduce later in this lecture. It's called pruning. So when you do pruning, which means if you have a weight matrix, you try to zero out some certain element at a certain location, which means these elements will kind of lead to invalid computation because the result is ending with 0. So this is we call this tensor core is designed to accelerate this kind of sparse matrix multiplication, which kind of only designed or leverage to kind of perform the valid computation in this sparse matrix multiplication. And we will come back to this topic later. And the fourth generation, they have more aggressive improvement. For example, they have a TMA, Tensor Memory Accelerator, which is dedicated for the tensor memory movement. And they also introduce this WGMMA, work group level and synchronized matrix multiplication. So if you compare these 4 times 4 times 4 matrix multiplication, later on, they actually have some work grouped matrix multiplication by supporting a larger number of matrix dimension. So there are different features of tensor cores. And apart from the evolution of tensor core, you can also see the evolution of the precision format. For example, originally, like the GPU, NVIDIA GPU 10 years ago, they only have like IEEE standard FP32 or FP64. Now they introduce some different data precision tailored for AI workloads. So the first one is the TensorFloat 32. So it's kind of have the same range as the FP32. However, because in here you can see the exponent range is the same as FP32, but they kind of reduce this mantissa to 10 mantissa. So the reason why they designed these TensorFloats 32, TF32, is because they found for AI workloads, it doesn't need to be very accurate. They can kind of sacrifice some precision. But for AI workloads, they still need very wide range, so they keep the range the same as the FP32. And the benefit of this is, if you look at this number of bits in TF32, it's kind of 19 bits, right? And if you look at the original, if you compare this with the original FP32, it kind of reduces some like memory bandwidth to kind of improve the efficiency of your memory transfer, which I already gave you an example before. And apart from this TF32, we also have microscaling FP4, which is called MX FP4. So the key idea of microscaling FP4 is they have introduced the idea of the shared scale. So originally, each elements, they have their own exponent bits, right? So like the kind of the range of the number they can represent is limited. However, in the MX FP4, they kind of introduced an idea for every 32 numbers, they also have another shared exponent, which means you can actually kind of have a wider range of representation. And in this lecture today, we will not introduce this in detail, but in later on we will have another module called, another lecture called Efficient ML. So I think it's in week 6. So we will introduce these different data types together, including the TF32 and MS FP4, and also the NVIDIA FP4. So we are currently actively being used for different models. For example, for this MX FP4, if you realize OpenAI last month, they realized their GPT OSS model, which is an open source large language model, they actually support this MX FP4. So yeah, so this is just some emerging precision And the last is the matrix multiplication examples. I received some feedbacks last time when the students are saying we need a concrete example to help you to understand the high-level concepts. So in here, we use the matrix multiplication to help you to understand how the CUDA programming is done. So this is just an example, which means the code itself might not well optimized, but we will introduce the key idea here. So let's, before we start the coding, let's just look at how this matrix multiplication can be formulated. Let's assume we have two input matrices, A and B, and we have out matrices, C. So when we do this matrix multiplication, we assume we kind of get one row from matrix A, multiply with one column of matrix B, and we do this dot product to get this one output points. So this is how we do this matrix multiplication, and we just do it multiple row by row, column by column to get all the elements. So this is the mathematical formulation, and here is the dot product because we kind of accumulate. We have the scalar multiplication, and we kind of accumulate in the intermediate results to get the final answer. And before we introduce this coding, this is the tradition. There's a convention we need to know, which is the data formats in CUDA. So there are two types of data formats in different programming language. One is called row major format, and the second one is called column major format. For row major format, it means the elements are stored continuously in memory, row by row. So here I give you an example. Let's say we have a matrix, let's say 2 by 2, 1, 2, 3, 4. So in row major, which means if this is your address space, continuous address space, so the storage in a row major will look like 1, 2, 3, 4. This is the row major, right? Because it is stored like row by row, right? So this is the row major. In the column major, it will be different. For example, in the continuous address space, it will be 1, 3. It's column by column, 1, 3, 2, 4. So they are representing different data formats. And in this module, we use the row major format. And one thing I want you to notice is this indexing formulation, because we will use data when we do this matrix multiplication, is basically calculate output matrix C in the row major. So in here, we assume X representing how the numbers of rows. So it's like the vertical dimension, remember. And Y denotes the number of columns, which is the horizontal dimension. And this is kind of different from how the thread index increasing and how they form the warps. So we will introduce this later, but now please pay attention to the Y and X for the matrices and your thread index. So let's start from the naive matrix multiplication implementation. If you remember, I told you the idea or the philosophy of CUDA programming is, let's assume you have a computation. And what you need to do is, first, separate this computation into multiple massive parallel computational tasks. And basically what you will need to do is assign each computational task to each thread. So this is what you need to do. In the case of matrix multiplication, a natural way to split this computation is, because we have different output matrices, right? A naive separation is we assign the computation of generating one output point in the matrix to one thread. So this is the programming idea we have. So we assign one thread to calculate one output point in the output matrices. So to do this, first, again, so we do this configuration setup I introduced before, right? So we kind of separate this thread into 32 times 32 thread blocks, and we calculate how many thread blocks we have in this grid. So this is a configuration, and we have these 2D global coordinates. So in here, we just use the naive way. We'll assign the x as the global context of x, and y as the global 2D coordinates y. So this is less optimized, but this is the one of the straightforward way to implement this, right? So we translate this thread indexing to the 2D global coordinates. And next, remember to perform this matrix multiplication, remember what I said, to keep the output matrices as a row major. So what we have is we have this indexing here. If you go back to a few slides before, this index here, to keep the output matrix also in the row major. So we have this indexing here to calculate the output matrices. And the computation is like we multiply alpha with these temporary float variables, which is the result of one output data point. And we multiply this beta times the original value already in these C matrices. And in this case, we assign this as 0. We assume this is 0. So we only need to care about how to get these temporal float variables, because this alpha will be passed in as a parameters. So to get these temporal variables, we write this code, this part, as here, right? So basically, if you recall the dot product, what we need is one row from matrix A and one column from matrix B. So if you look at this index, it's exactly to get one row from matrix A. And because if you remember, X denotes how many rows, right? So to get this position of X, what we need to do is we multiply how number rows we already have with the number of elements in each row, and we kind of do this increase by I. So the I is the inner variables we iterate through this one row, right? And for B, remember we need one column from B, right? So every time we need to jump one row in the matrix B to get the number for this inner loop. So basically we multiply I times N, and N is the number of rows, the number of elements in one row in matrix B. So they are representing the row axis and the column axis. So remember this. And we kind of do the dot product to get the result of these temporal variables. And we kind of assign these temporal, or multiply these results, the result of dot product with the alpha, and to get the final result. And when we put everything together, we will have this kernel function. So feel free to try this. And however, here we will try to analyze what is the problem of this kernel implementation. The problem of this kernel implementation comes from the convention of how thread ID increased and how warp are grouped in this thread ID space. So here is how it looks like. So let's assume, so first what we want is we want to analyze the data access, right? So to understand this data access, we need to know how the thread ID are grouped together to assign as one warp. Because we mentioned before, one warp will kind of do this the data movements together. So let's say in NVIDIA CUDA programming, we have the continuous threads. We have these continuous threads along the x dimension. Along the x dimension as one warp. So to illustrate this idea, let's look at this slide. So this is your thread ID. Sorry. So this is your thread ID x. So you have 1, 0, 1, 2, 3, right? and you have the thread ID Y. So like this. So basically, how warp is grouped is they will help group the thread along the X dimension first. So which means if here the warp size is 8, it will only address this as warp 0. However, in here, because the warp size is 8, so you have to have these two consecutive thread IDX together. This is clear, right? So this is a warp size, and group together first according to the thread ID along the X dimension and then Y dimension. So we have this. And if you look at this example, if this is how our thread blocks increase. So if we have these thread blocks increase along the X dimension first, so which means it will go along this direction first, right? It's equivalent to calculate outputs along the column dimension. This will cause problem about the memory efficiency. So one example is this part clear? So if we increase the thread index X by 1, and if we look at here, if the X increase from 0 to 1, it equivalently adds n numbers of n. And this n equivalently means the first element in the second row. So basically, if we use this tradition to group the thread ID together as a warp, it means one warp will calculate one column of the output matrices. And this will cause problem what we call memory inefficiency. So let's look at what we want as the ideal case. So as I mentioned before, the memory movement of warp, we usually want it to have the consecutive memory access, which means, let's say this is the warp 0. What we want is, for each thread in this warp, we want the data elements required by each thread, they are in the consecutive address space. For example, here. This is an ideal case because, as I mentioned before, for example, this is the memory. Let's assume this is global memory, right? So what we want is, because we have the transaction size constraint, what we want is we want warp 0 to access a large transaction size, and every element in this one memory transaction, they are flowing into a continuous memory space such that we can maximize this memory bandwidth. So, however, in the case of this naive implementation, if we recall here, so according to the increasing of this thread ID, we are actually, the computation order of output matrices is column by column. So which means each time we will need different data in this memory address space. For example, when we compute this, yes. So, for example, in warp 0, right here, this data is required to compute these elements. However, in the second thread, because second thread is assigned to compute this red part, what we want is the first element in the second row, which means for this warp, we actually want to access the data from this matrix A column by column. However, A is stored in a row major, which means we are not like accessing data continuously. It kind of hurts the memory efficiency. I hope this is clear. So to do this, we can do some small trick, which means we change how this thread ID is mapped to this 2D global index. Use this block size trick, which means in the original case, if you look at here, when we increase this thread block, we increase this thread block. So we are trying to accumulate the elements in the column order, in the column by column dimension. However, if you do this trick, you will realize. So now you are trying to kind of compute row by row. This is clear, right? Because you're trying to, if you try to put some real number into this indexing, you will realize, let's say if you thread index x is increasing, for example, from 0 to 1 to 2, and this x keeps staying the same, right? Because this is the division. So which basically means you will stay in the same row. And when you increase this thread index x, because this equation, you basically try to increase x, so it means in the same row we keep iterate along the row dimension. So this is the memory collapsing. So the general process is every time when you have a CUDA program, what you need to do is first you need to separate or kind of think about how your computation can be separate into multiple small tasks and how these small tasks is mapped into different threads. And you also need to have this data layout in your mind to see, okay, whether this memory access is continuously or not. If that is not, you will need to kind of manipulating on this thread ID to this index transformation to have some trick there to make the data access continuously. And one question some students might ask is, in here, can we address this memory inefficiency by just swap in this naive implementation, by just swap this assignment. For example, we're assigning this line of thread to x, and we assign this thread indexing to y. It can also address this memory collapsing issue. And the reason why we have this memory issue is caused by the different convention of x and y. So in here, we assume x goes along the vertical dimension and y goes along the horizontal dimension. However, when we do this thread indexing, we notice x is along this x horizontal dimension, and y is going this vertical dimension. So this is all the problem caused. And if you kind of cross-assign different numbers, you can also address this problem. And so the reason why we use this block size trick is because it can enable more optimization later, so which we don't have time to cover in today's lecture, but I strongly recommend you, if you have time, read this link. So it kind of gives you step-by-step optimization of how from this naive kernel to like enhance with the memory collapsing and shared memory caching, also 1D block tiling, 2D block tiling. Because before we introduced these tiling techniques, right, it can kind of maximize the data locality. So by using this block size trick, we can kind of facilitate us to explore more and more computation. And if you are interested on more advanced GPU optimization, I strongly recommend you to refer to this link. They have a very good animation and actually some kind of figures I adopt from this web page. And this is all for today's lecture. I don't want to keep you for too long, but let's just help to recap what we have covered today. So the first part, we covered why we need GPU. So to introduce this, we let you know like the AI demanding a large amount of GPU computing, and we introduce some taxonomy, which I hope you to remember. The first is 3 levels of parallelism. In instruction level parallelism, thread level parallelism and data level parallelism. And we also introduced the microplanes taxonomy, which is very famous. SISD, SIMT, MISD, and MIMD. So we are representing different parallelism along the instruction level and data level. And we introduced this programming model using the thread block, and grid in this CUDA programming, which is a variant of SIMD. So we call it SIMT, single instruction, multiple threads. And in the microplanes, it's kind of a variance of microplanes, single instruction, multiple data. And we also introduced this CUDA architecture. So the reason we introduced this CUDA architecture is help you to understand the underlying hardware detail of GPU, and which can help you to understand why, for example, why this memory collapsing can help to improve the performance. And we also introduced different memory hierarchy. As I mentioned, they are forming a trade-off. For example, for global memory, they have the larger transaction size, but they have the lower data access latency, and also they have a larger memory capacity. And one key problem when you do this CUDA programming is how to allocate your data into different tiers of memory. So you always have this threading in the memory layout in your mind to optimize this CUDA kernel. And we use this CUDA example to introduce the naive implementation of matrix multiplication. And because the limited time of this lecture, we are only able to cover this memory collapsing. And if you have time, I strongly recommend you to read this thing I put here. It can kind of facilitate you to, if you have time, just read it, and because it will kind of facilitate you to do coursework later very well. So yeah, this is today's lecture. So if you have questions, just come to the front.
I think I'm seeing videos might help as well. Yeah, I close my eyes and I sides. It's time to read. I'm frozen. Memory access. I like it. Right? I gotta mute the same element. I do like baby sandwich too.
The course is all prerequisite.
It's waiting. Yeah, I found that one too actually last time. Same product. It's like nowhere to sit. Contiguous. Try the do the reordering. Or your active might be contiguous and therefore can be covered as. One lecture came to the. Yeah, no.
I mentioned before.
Yeah, exactly. It's the way that we use it to visualize everything.
You got lots of.
Yeah, I think.
High budget order, expenses calculate session.
Yes, exactly. Basically, you control. For example, in my example, I use a for each thread. But you can just have one simple addition. It's up to you. It depends on how you kind of assign this addition to one thread. It's kind of very flexible.
And the concept of warps. You say you have one dot product in one thread, and then you have 32 dot products that would make one warp. And one warp also goes into one cuticle. Why would you do that?
No, so one warp usually one thread usually goes to one cuticle. Let's say if you have 32, in most cases you kind of launch 32 cuticle.
Okay, so one warp.
Yeah.
Threads usually goes to 32.
Yes. Usually, it depends on how you map this, and there's some different tricks in existing CUDA program.
Okay. Okay. Excellent. Thanks.
I hope this today is clear.
Yeah. Thank you.
Yeah, I'm just mainly concerned about my matrix multiplication example. I hope this is clear.
Yeah, I think some of it was clear, but some part was. Yeah, I wanted to ask more about the memory coalescing. Like, I understand why the naive optimization is so naive, but it doesn't work because you need to have a memory access for each of the things in the column. But I didn't quite understand how reordering works.
You mean the after block size?
Yeah. So you would just in the naive implementation, you would just go axis this way and y this way on the thread.
Yeah. Yes.
And then how does it differ from
So it basically just control how the thread is mapped to your 2D global coordinates. But originally, so you have these threads. Let's say if your thread, usually the thread goes into this direction, right? This is x, this is y, and as I mentioned before. And when you go to one-to-one mapping, when your thread goes to this direction, your output matrices is going to this direction. If you remember. And now, if you kind of reverse it, if you kind of go into this direction, it means so your output matrices, the completion order, will be in this dimension. And when you have this kind of order, so you only need to access one row from A, and you kind of access row by row from matrix B. So this is how the
it's basically just the way how we
map
actual matrix multiplication, but in this case it's just the order
of yes.
Okay, nice, thank you.
Okay. Yeah, sorry, I think I thought I mentioned this. Perhaps I should make some animation to explain this better.
Yeah. This graph kind of like.
Okay. I will put this.
I missed it.
I want to ask if you're programming thread level, but the warps are 32 threads. How does that work? Because you don't really program thread level, right?
No, you program at thread level. Why you don't?
Because I thought warps are the underlying representation.
Yes.
So even though you would program at thread level, it would go into a warp, and the warp would distribute it to other threads.
No. So one warp, they will always execute the same instruction.
Okay. Yeah. Okay. Yes. Okay, and then based on that, the conditionals.
Yes.
Oh, okay.
Okay, that part, yes, I forgot to mention this. Yeah, I will need to. Okay. But yeah, I will try to explain this in the tutorial. I believe some students may also curious about this.
Yep.
Thank you.
No questions.
Like for this lecture, right? What do you think you roughly the examiner? How will we ask?
I think there are multiple ways, right? So I can give you a CUDA code and ask you to analyze the inefficiency and ask you to propose the optimizations in small way. Yeah.
Oh, okay. But would you test something like matrix multiplication? Or?
Basically, it will be all the focus on, I think, matrix multiplication. So I think even just for simple matrix multiplication, is already a lot of things to be done for CUDA. If you look at the last line I put, there's a link introducing different optimizations. The 1D block tiling, 2D block tiling, a lot of optimizations to go. So it's already enough. Even just simple matrix multiplication, a lot of optimizations.
I see. Okay. It's quite interesting.
Yeah. I think. I think some key points I forgot to mention. Today, like one warp there, kind of sharing the same instruction, and this kind of increasing direction of flop. Yeah.
Do you have any ISO?
No, I don't have.
Oh, you don't have. But because I know one girl that is doing MRES and she's doing with you, right?
Yes.
Oh, but this semester, this term, you don't have.
No. But MRIs, they don't do ISO, right?
Yeah, I don't think it.
MRIS is different. They only have one research project.
What about the independent
individual? I think that will come later this year.
Oh, so you're not sure yet?
Yes, we might release some project related to CUDA programming.
Oh.
Yes. I think that will be decided later.
Oh.
Yeah.
Okay. Okay, great.
Okay, thank you.
Thank you.
Yeah, this is Rob.
Okay.
Sorry, I will correct this.
And just for the thread TLP versus ILP. From what I understood, the threads are multiple instruction.
Yep.
Okay, so this would be like this is one operation. So for example, additions made in parallel, and this would be, for example, load the data to the addition.
No, it will be just like for you have multiple threads, and each thread they will have different instruction string, which means sequential instruction string. So it's just the example of the matrix multiplication. One thread, it kind of will be in charge of calculating or generating one output point in your output matrices. And to get these output points, you will need to do a lot of matrix multiplication. You will need to do dot product, do a multiplication of your accumulation of these things. So this is actually multi-threading. So one thread can contain, let's say, 10 instructions or 20 instructions. The instruction string is sequential. Okay. Yes. Is that clear?
Yeah.
Okay. And do you think the matrix multiplication example is clear to you? Or
Yeah.
Okay.
Yeah, I think.
Thank you.